This lesson is about polynomials. Let's start with a monomial. A monomial is essentially the product of a number, which we call the coefficient, times a variable, which we don't typically know the value of, raised to some power. And these three things put together form a monomial. Here's another example. Now, sometimes a monomial has a blank coefficient in front of it. When that's the case, we can consider that a 1. Here the variable would be x, of course, and the power would be 2. Here's another example. In some monomials, we have a visible coefficient, in this case 4, but our variable has no power or exponent above it. In that case, it's also assumed that the invisible exponent is 1. And even ordinary numbers like 7 are considered monomials. Where 7 is the coefficient, there's no variable, but we call this monomial a constant. And we're also considered to be the 0-degree monomial because there's no variable at all to give it a degree in the first place. Just a vocabulary here, when we have a third-degree monomial, we call it a cubic monomial. A second-degree one is called a quadratic. One with a degree of 1 is called linear. And as we mentioned before, if there's no variable at all and the degree is 0, we call it a constant monomial. So if you take monomials and you were to string them together with additions and subtractions to make a sum or difference of monomials, we call this a polynomial. Here's another example of a polynomial. We call this one a trinomial, which is just a word that means it has 3 terms in it. Notice it has the 3x squared, the 2x, and the negative 5. If a polynomial has 2 terms in it, we call it a binomial. And as I mentioned, a 1-term polynomial is called a monomial. Now, all of these are considered polynomials because a polynomial is essentially one or more monomials added or subtracted together. Let's talk distributive property. Distributive property reminds us how to multiply a number times a polynomial. So you'll notice the 2 outside of the parentheses here. In the parentheses is a polynomial, and when we multiply, we simply multiply 2 by every number or by every coefficient in that polynomial. Like terms. These terms, these monomials essentially are identical. Of course, they're alike. But what does it mean for terms to be alike? Those clearly are the same. But how about these terms here? Are they alike? Well, they have something in common. They both have a coefficient of 8. But we don't consider them like terms. Why? We're about to see. Look at these 2 monomials. They also have something in common. But what they have in common is their degree. They're both third-degree or cubic monomials. So we consider monomials alike if the degrees match, as they do in these 2 cases here. So for us to call 2 terms or 2 monomials alike, or in other words, like terms, the degrees have to match. Let's look at combining like terms. Before we do, this polynomial here you can see has 4 terms, but notice that all the degrees of each monomial in this polynomial are different. We have a 3rd degree, 2nd degree, a 1st degree, and a 0th degree. In other words, we have a cubic, a quadratic, a linear, and a constant term in this polynomial. And notice that they go in order from highest degree to lowest. When a polynomial is written this way, we call it standard form. But this second polynomial here has the exact same terms as the one above it. And these 2 are the same polynomial. But we say that the top one is written in standard form and the bottom one is not, because essentially it's not in the traditional order of highest exponent to lowest. Now this polynomial, you'll notice the terms are not written from highest degree to lowest. This is definitely not in standard form. But furthermore, we're going to discuss the issue here of combining like terms. These two terms in this polynomial are alike because they're both second degree terms, and therefore we can add them together by adding the coefficients. The first one has a coefficient of -3. The second one has an invisible coefficient, as we call it, or the coefficient of 1. And when you combine the -3 and the 1, you get -2. And therefore, these two terms combine together to make -2x squared. Notice that we combined the coefficients together, but did not change the degree of the monomials. In other words, we added two second-degree monomials together and we got a second-degree monomial. You'll notice this term here, this cubic monomial, is the only third-degree or cubic monomial in the polynomial. There's no other x cubed anywhere to combine it with. I will essentially leave that alone then and preserve the value of the polynomial by bringing that term down, as it were. These terms here, you'll notice, are also alike. Why? Because they're both first degree. They both don't have an exponent. And because they're both first degree or linear, I can combine them by combining the coefficients. I combine the 5 and the -2, and I get +3. And lastly, this term here is constant, but it's the only constant in the polynomial. So if I sort of carry that down into my next line, I'm preserving the value of the polynomial. And now these two polynomials are equal to each other. But which one is in standard form? Well, it turns out neither until I switch these terms around. And now this second polynomial here is equivalent to the one above it, but it's a more simplified version because it's in standard form. By the way, when the leading coefficient of a polynomial is positive, we traditionally don't write it, and it's assumed to be positive. It's just less for us to look at. So that problem shows the method of combining like terms to simplify a polynomial. Let's look at an addition problem. Here we have a polynomial plus another polynomial. Before I do this problem, I'd like to go back and think about some basic math in relation to parentheses. This is not the problem we're working on now, but if you look at this problem here, you'll probably remember that to work this out, we have to do the mathematics that's inside the parentheses first, sort of the order of operations concept. So if I work out each of these parentheses, this is what they work out to if you add the numbers together. And so this mathematics problem simplifies to 22. Now this shouldn't sound unusual or different to you, but what's worth pointing out here is this. If instead of working out the parentheses individually, as the order of operations would have had us do, if I simply ignored the parentheses and added those numbers up, I would still get 22. Am I saying that in a mathematics problem you can ignore parentheses? Well, generally no, because parentheses are an indication of what gets done first. But notice, in a problem that is pure addition, it wouldn't matter if I ignored the parentheses. And that's an important concept here, because here I have an addition of polynomials. And when you have that, for the same reason, you can essentially ignore the parentheses and then combine like terms. So let's go about the business of combining like terms. This ends up being the result. I'll show you where I got this from. The first thing I noticed is that I have an x cubed. It's my highest degree term, and so I like to list that first, but it was the only x cubed or cubic term in the problem, so I simply carried it down because there was nothing to combine it with. Likewise, I brought my x squared term down because it was the only x squared term in the problem. However, we do have two linear terms that are combinable, 11 plus 5 is 15, so those terms combine that way. And likewise, there's two constant terms here, which are also combinable to make 3. So essentially, when you're adding polynomials, you just disregard the parentheses and combine like terms. And now we have our answer in standard form. Let's look at subtraction. One thing that's not often thought of in a subtraction problem, that should be, is that fact that subtraction is really a hidden multiplication problem. Now, that seems strange because when we learn subtraction, nobody tells us it's a multiplication problem in disguise. But in algebra, it's important to think of it that way. When you see an object minus another object in algebra, that second object is being multiplied by -1. That is the actual meaning of subtraction. And so it's maybe not necessary to write this all out, but when you see that subtraction, you should think of it as a multiplication by -1. And when I multiply the -1 using the distributive property through the parentheses, notice the change of sign of all of the coefficients in the second polynomial. So essentially, when you subtract polynomials, you're in some way distributing that negative through the second polynomial. Ignoring the parentheses on an addition problem like I can do, I'll do that. Notice I left this as adding a negative. You could just have written that as subtraction if you'd wanted to. But now we're not done because we're not in standard form. And to get there, we should combine like terms. Here's the final answer. I'll show you where I got that. First, I combine my cubic terms, the first of which has no coefficient. So I considered that a 1. So 1 minus 6 is -5. Therefore, those terms combine that way. Then I moved on to my quadratic term, which I only had one of, so I carried that down. I only had one linear term, so I carried that down. And my two constant terms were combinable, therefore I did. 5 minus 8 is -3. And now I've taken a polynomial that's not in standard form and simplified it or reduced it down to standard form, a more acceptable version of the polynomial. Sometimes a polynomial problem will have multiplication and addition in it, or even multiplication and subtraction. Now you don't see a multiplication sign here, but it's assumed that there's a multiplication between the parentheses and the numbers in front of them. So what do we do in the order of operations when we have two multiplications and an addition in the same problem? Well, as you'll recall, multiplication comes first. So I did this multiplication using the distributive property, and I did this one likewise. And now I've done my multiplications, I'm ready to add. Well, adding polynomials amounts to combining like terms essentially. So let's go from highest degree to lowest. My highest degree term was my -4x squared. It was the only quadratic term in there, so I carried it down. 5x was my only linear term in there, so I carried it down. And my two constant terms were combinable, which I did. -15 plus 4 simplifies to -11. And there I've put my polynomial in standard form again. That's essentially how to add and subtract polynomials. But let's go one step beyond the problems. Now, what you're about to see, you would probably not ever do in a mathematics class, but it'll give us a proper perspective on what polynomials actually are. In this video so far, we saw this being written in standard form that way. We did this problem, which worked out to that. And each of these green boxes are the problems we've already seen in this video. And each of the yellow things, it's very tempting to think of those as the answers to those problems. And if you're in a mathematics course and you're taking a test, then this is the traditional way of thinking about it. Everything in green here is a problem, everything in yellow is an answer. But let's go beyond that and think about what we've actually done here. I'll take this one as an example. What have I taken a mathematics problem in green and put the answer in my yellow box here? Well, that would be the way we would often think about it inside a mathematics class. But let's go beyond that thought. What if I were to take these two polynomials, which I'm claiming are equal to each other, and what if I were to substitute or plug in some random number for x? By the way, I'm not suggesting you would do this. In a mathematics course, you would not take your problem and answer, your so-called problem and answer, and just plug a random number in them. But I'm doing this as a thought experiment to give you a broader perspective. If in each of these polynomials x were 3, then I could simplify each of these down to a number. If you want to follow every numerical detail, pause the video. But the bigger picture here is that this first mathematics expression would simplify to 87 if x were 3. How about the second one? If we simplified that, we would get the same number. And by the way, this is not a coincidence that it just happened because I picked the right number. Any number I had chosen, whether it's 3 or anything else, would have had these two polynomials having the same value. Now, even though we don't ordinarily think about it, the x's in polynomials do represent numbers, and I'm simply suggesting that if x represented some random number of my choice, these polynomials have the same answer. And furthermore, that would always be the case regardless of my choice of x. So rather than thinking of this as a math problem and a math answer, which we tend to do, think of it as two polynomials. One of them is in standard form and one of them isn't, but they're equivalent, meaning whatever x were, they would have the same value. And that concludes the lesson.